Welcome back. We're starting very shortly. Okay, so we're back. Let's continue. What we're talking about? We're talking about families of modern operating systems, right? So we know already that Linux is not the only Unix-like operating system. There is also a BSD family and some less important ones, which is Sun Solaris, which is now Oracle Solaris, maybe others. Okay, so I'm not talking about Windows and will not be talking about Windows in this course, but we'll be definitely talking about Linux. Well, what is yet another very popular operating system which you can find in uh, consumer notebooks and desktop computers nowadays?
Mac OS or
Yeah.
OS X.
And that is a very interesting story, actually. So what is Mac OS inside? It is a very interesting hybrid. So first of all, uh, Mac OS is the whole operating system which is more than the kernel. Um, we did not provide a full structure of what the operating system is, so what it contains. So we already know that there is such a thing as a kernel. Um there is a special name for the kernel of macOS. You would not be able to see it directly in macOS, yet it has a name. Anyone knows how the kernel of macOS is called?
Darwin.
Sorry? Darwin, yes. Okay. And then, apart from that, multiple other components, so we may at some point have a look of them. So the kernel is indeed called Darwin. What what is it all about? The Darwin kernel contains some elements of BSD. For example, components such as file system, network communications sockets, um, some other top level component, they come from FreeBSD, actually from FreeBSD. So even if you do not use FreeBSD explicitly, uh, it is by far superseded by Linux, both actually on the server side and on the client side, although some high dependability servers, for example, they still run FreeBSD in preference to Linux for some reasons. It is very, very, very reliable and robust. Then still you use elements of FreeBSD if you run macOS. But there is another pedigree in Darwin, which is not coming from FreeBSD. There is a very interesting family of operating systems, and that family, I would say, has a direct relevance to our formally verified operating system model, which is called Mach. Have you heard about Mach? Mach is a Carnegie Mellon operating system from Carnegie Mellon University, which appeared around 1988. So what is so popular about, so important about Mach? Well, taking a step back, we're talking about this BSD, University of California, Berkeley, BSD family of operating systems. So what is important about BSD? One of those early systems, which was called 4.2 BSD, there was a system like that, and that was 1982, was the first system with really TCP/IP communication stack. And as an API to this TCP/IP communication stack, sockets appeared there for the first time. So all things we're currently using, they're actually quite old. Imagine that sockets first appeared in Berkeley system distribution, in Berkeley Unix, in 4.2 BSD 40 years ago, nearly 40 years ago, in 1982. And the socket API, by a large extent, is unchanged. Well, obviously, there are many more options now, but the whole idea that, first of all, TCP/IP stack would be implemented inside the operating system kernel, and that's a very important point. And secondly, yes, the endpoint, the API endpoint for TCP/IP communications is called a socket, which acts like a file descriptor that you can create it, you can connect it, you can bind it, and then you can write and read the data through the circuits. That was all appeared there. Okay. In a similar way, there is another very important programming entity which we use in our application software development, I wouldn't say every day, but use it very, 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 very commonly. And I'm talking about threads. Do you have any experience with multi-threading and thread programming? And do you understand the difference between threads and processes in an operating system like Linux?
Can you explain it?
Okay, but you probably have seen them, right? So basically, threads and processes, we're talking about Unix-like operating systems, threads and processes, they're units of concurrency, which means if you like to create two pieces of code which would execute notionally concurrently with each other, why I say notionally concurrently with each other, it may be that they will execute truly in parallel, for example, on a multi-core CPU or on a multiprocessor system. Then they really run on different CPUs, on different cores, and they really run concurrently, run in parallel, we would say. Or they would really run on the same CPU if you have only one core, but interleaving with each other. One stops, another one executes for a very short while, maybe just for a fraction of a second. Then the control is given back to the first one. It is called time slicing. So concurrently means either really in parallel or through time slicing, through some kind of preemption. One entity stops, another one starts and runs in its stead. Then the second one stops and the first one runs. But if they are interleaved frequently enough, for an outside observer, it looks like uh, they run really in parallel. So concurrency and parallelism are slightly different things. In the Russian language, there is even no direct equivalent to the word concurrency. We call it parallelism in both cases, but in fact, concurrency and parallelism are quite different things. So parallelism is a true concurrency, whereas concurrency by itself may be through time slicing. And still, although obviously in that case you do not get any performance gain, but there are many algorithms which, for example, those which involve network communications, which benefit from uh, concurrent, apparently concurrent execution. So, for example, one of them is waiting for new data to arrive over the network, so reading from a socket. There is no data, so that unit of concurrency sleeps. It is descheduled, it sleeps. The other one is doing some useful work at the same time. It runs. Then the data appears for the first one. The first one wakes up, preempts, so takes the CPU from the second one, and so on. So even if we have only one CPU, we may still benefit from the concurrent model, in particular if our model involves external input-output, which takes time, and even more specifically if it involves network-based communications, for example, waiting for data to arrive via a socket. And processes as units of concurrency or concurrent entities have been in Unix systems from the very beginning. When first Unixes appeared more than 50 years ago, as I said, in around 6950, oh, sorry, 6970, 1969, 1970, then it was already possible to create processes and run multiple processes on your system. Again, the systems were typically uniprocessor one at that time, so those processes were running concurrently, but not truly in parallel on those systems. On modern systems, multi-core CPUs and large-scale multiprocessor systems, they may run truly in parallel. Threads, on the contrary, is a much younger concept, and threads are lightweight processes. So the difference between process and threads is about how much system resources they would use in order to be created and to run. So threads are approximately, we would say it is a lightweight process. What does it mean lightweight? The major difference between threads and processes is that threads are running in the same memory address space. Multiple threads run in the same, may run in the same memory address space. So I would diagrammatically explain it in this way. So for example, there is a process one. There is a process two. They all, one way or another, in modern operating systems, are isolated from each other. It means that if there are several, let's say, variables which are present in our programs running as process. So this is some program, this is some program. It could be actually exactly same executable, but two instances of this executable. There is a variable x here, there is a variable x here. These two variables x are completely different. First of all, they are different because they are related to completely different locations in memory. And secondly, any program entities running in process one, they can't see anything which is in the address space of process two. So the operating system runs them in such a way that their memory images are completely isolated from each other. It is not possible by using a wrong pointer arithmetic in process one to damage any data in process two or other way around. So they are isolated in memory. How it is done, there are several techniques of how this could be done. In modern operating systems, this is typically done through the mechanisms of virtual memory. Don't confuse virtual memory with, let's say, virtualization of CPUs, which is a completely different concept. Virtual memory simply means that each process is given a certain virtual address space, but it is mapped, first of all, dynamically, and secondly, it is mapped to different physical memory segments, so that if your pointer arithmetic points somewhere, it points only at something within your virtual address space. Another process completely runs in another virtual address space, and all memory addresses are specific to that space. So whatever you do with the memory, you wouldn't be able to access or harm or damage or improperly read maybe some security safe, security sensitive data from the address space of another process. Well, in theory, at least. Whereas threads are lightweight processes running within processes. So within process one, there are multiple threads running here, and within process two, there are multiple threads running, and they run conceptually in the same address space. So all process-wide variables, or memory locations more specifically, are visible to all threads. So all threads can interact with this variable x if this variable x belongs to the whole process. Having said that, it is possible to create local thread-specific storage in the threads, which wouldn't be visible from other threads, thread local storage or thread specific storage. That's possible, but a priori, process wide memory is visible for all threads. So if we can say more formally, so process is a unit of a resource utilization or resource isolation. CPU, memory, file descriptors are per process. So if you create a file descriptor exactly with the same number, 0, 1, and 2, where 0 in Unix means standard input, 1 means standard output, and 2 means standard error, then these file descriptors within one process and with another process mean completely different devices. So for example, your standard output can be directed into one file for process 1 and to completely another file in process 2. File descriptors and so on are different between processes. Whereas threads are just units of concurrency. All other resources, that's important, are shared between threads. In particular, file descriptors are shared, memory is shared. The same memory location is accessible for both reading and writing from multiple threads. If a file was opened in one thread and the file descriptor is written in variable x, then another thread can write data into exactly same file, and if they do it, I would say, improperly, then garbage can occur in the file because one thread starts writing something, didn't complete, another thread puts another data, then the first thread continues, so there would be interleaved and probably ill-structured and invalid data output as a result. But on the other hand, creating threads is typically a less costly uh, less costly operation. You can create typically a large number of threads. They're reasonably lightweight, so that really multiple threads can coexist within your application. So once again, processes are units of concurrency and resource utilization, primarily resource utilization, whereas threads are only units of concurrency. We may encounter both processes and threads many times in our course. So as I said, processes have been with Unix type operating systems since the very inception. But uh, they appear to be relatively heavyweight and difficult to use units of concurrency. So, for example, if you um, run a computationally intensive application, and this application needs to do some, let's say, numerical computations concurrently, and they found a way of how your computation can be divided between multiple, uh, in this case, really parallel units. running in parallel. Then using processes to that end is very much inconvenient. Why it is inconvenient? Because you would, for example, you would need to, a very, very simple example, trivial, but it will illustrate the point. There are two matrices, matrix A and matrix B, okay? And what you simply need is to add up these matrices. Obviously, matrix addition is a very simple operation, taking, of course, provided that they have equal dimensions. We take the corresponding element ij from one matrix, we take the corresponding element ij from another matrix, and the sum of matrix A of ij plus matrix B of ij would be the resulting entry of the sum, all right? But if the matrices are really big, so for example, I don't know, 1000 by 1000 each, such matrices do exist, then we can run multiple, as I would say, units of concurrency, which units of concurrency we'll now see, which read matrix A and matrix B entries independently and fill in the corresponding entries in the sum. But in order to do that, both units of concurrency, which operate on matrix A and matrix B, must be able to see both actually matrix A, matrix B, and the result. So a parallel entity takes a particular subrange of indices from this matrix, a particular subrange of indices of that matrix, and produces the corresponding subrange of indices of the resulting matrix. So both of them, both units of concurrency, needs to see the first one, the second one, and the result. To have at least a read access to the first and the second one, and at least a write access to the resulting one. Processes are not suitable for this task because, as I said, processes operate in completely isolated virtual address spaces. So the views of matrix A, matrix B, and the resulting matrix C for each process would be completely different. They would not be able, working together, fill in the same shared between them matrix, the resulting matrix. Instead, each of them would have its own copy of the result. And if, for example, we do it, I don't know, using two processes, and the first one operates on the top half of all matrices, and so that's the first process, and the other one operates on bottom half of all matrices, then what would happen is that they would get two results. The first one would only fill in uh, the top of the result, leaving the bottom completely unfilled. The second one would only fill in the bottom one of the second instance of the result, having the top unfilled, because they operate in a completely separated environment, in completely separate memory spaces. So this is clearly not a solution. What we need to do is to be able, for our units of concurrency, to see all inputs and the whole result. And that's how they would both fill in different parts, but of the same result, of the same single result. And that can only be achieved using threads which share the memory space between them rather than processes. When the need for this type of concurrency emerged, and that was precisely in 1980s when more and more parallel hardware was coming into existence, and problems like even matrix arithmetic, very simple one which we have discussed, uh, started to become the real concern, then it was realized that processes operating each in its own address space are too heavy and inflexible units of concurrency in Unix systems, and they had to be supplemented by something. So that second entities are precisely called threads, which operate over shared memory, and that way they would very easily be able to do concurrently or maybe truly in parallel if parallel hardware is available this type of operation on large matrices A, B, and C. And charrettes were not first introduced in Unix systems. Charrettes first appeared, well, you can now guess where the charrettes first appeared. Looking at this picture, where do you think we had charrettes for the first time? In Mach. In Mach operating system, in BSD Unix, as we said, first socket API, in the Mach operating system, first charrettes. Although Mach is not used by itself nowadays, but elements of Mach, very significant elements of Mach, are now part of a Darwin kernel. So Darwin, well, at the time when Darwin was first created, that was in another operating system at that time owned by Steve Jobs, which was called Next Step. That was around mid 1990s. At that time, in mid 1990s, Mach was still a very young operating system. It was less than 10 years old. It was considered to be a very significant innovation in computer science, and that's why the internals of Darwin contains elements of Mach. So to be a little bit more precise, that's how Darwin looks like. There is an internal Mach kernel. Darwin is itself a kernel, but it is the kernel of the kernel. And it is responsible for two things actually. For precisely process and thread scheduling, or simply speaking, for everything related to concurrency, and for virtual memory management. And outside of that, that's how Darwin looks like. Outside of that, there are components coming from FreeBSD. FreeBSD itself appeared in 1993. Sorry, 1992. As we said, from FreeBSD file systems, network I/O, and some device drivers, whereas other device drivers are not present in FreeBSD and were developed specifically for Darwin. Okay, that's how it looks like. But Mach, apart from providing a very important technology base for Darwin and macOS, continued to evolve on its own. So this was, I would say, you see, in 1988, Mach was a very important source of innovation, very much like Linux was, very much like BSD, Unixes have been previously. And then Mach continued to evolve on its own. First of all, Mach is a concept which is called microkernel, and that's a very important concept. In Linux, the kernel is responsible for many activities. So it is really process and thread scheduling. It is all low-level controlling of devices through the device drivers. It is obviously network communications. It is even providing direct access to the hardware for graphics rendering, uh, security and cryptography component. So really many things are inside of Linux kernel. We'll have a look together at the Linux kernel. But this is why Linux is called monolithic kernel. It is a monolithic kernel all together. So all components just link together and they provide a kernel. Mach was the first implementation which provided a much more structured approach. So Mach by itself, as you can see, it is responsible only for process and thread scheduling and for virtual memory management. Everything else, like file systems, network I/O, and so on, can be implemented and is implemented in Mach as threads or processes are running on top of Mach. So basically, it is a kernel of the kernel and other kernel sources, other kernel services, which run as a kind of normal processes, providing essential kernel-like functionality. But at least they are not monolithic. They are very much distinguished between the kernel of the kernel and the core of the operating system and the additional services running on top of it. Then the microkernel philosophy. So split them, uh, delegate as much activity as possible to like normal processes. They are not completely normal because they are predefined in the operating system. So for example, if your process implements a file system, then you wouldn't be able to live with it. It's not like an application level process. Yet from the point of view of process scheduling and how this process lives in the operating system, it is more or less like a normal user level process. So Mach provided this type of structuring, quite a good structuring within the kernel, which is called the microkernel architecture. And microkernel architectures continue to evolve, and Mach evolved into an L3 Litke, L3 named after the German computer scientist who developed this family of kernels, and after L3, the L4 family of microkernels. There are many implementations of them. One of them will be of great importance for us in this course, which is called, in particular, it is called SCL4, which would be a part of our big attention, and I'm going to talk about it in significant detail. All of them are descendants of Mach. But on the other hand, Linux nowadays is also affected by the Mach methodology. Actually, at about the same time when Mach appeared, Professor Andrew Tannenbaum from University of Amsterdam, he created another microkernel, an operating system which is called Minix. Minix is not Mach. They have completely unrelated pedigree and completely unrelated code base. They emerged at about the same time, manifesting the microkernel based architecture. Have you heard about Minix and why is it important? No, you haven't? Minix by Andrew Tannenbaum. First of all, the emergence of both actually Minix and Mach in late 1980s and early 1990s manifested some kind of microkernel mania. So monolithic kernels at that time were considered to be something already very much outdated, wrong, and so on and so on. For example, monolithic kernels like BSD family of Unix were considered to be a dead end of operating system development, a wrong thing. So people were thinking Mach and Minix are right, and Andrew Tannenbaum, by publishing his very famous series of books on operating system design, he retired not so long time ago, but before that, I think he published 4 editions of his very famous book, which, if you're interested, I will uh, drop to our Telegram channel. They are very instructive to read. We may use some material from them just to understand what microkernels are about. So let's say early 1990s, everything was saying old Unix, in particular BSD Unix, is wrong, long live microkernels. Or up with microkernels, down with monolithic kernels. At that time, Linus Torvalds was thinking about starting his work on Linux. Actually, there might be no even direct need to create Linux because BSD was already widely used at that time, but there was a risk that AT&T, you remember, everything started with AT&T Unix, that AT&T could file a lawsuit against BSD for allegedly reusing some kind of AT&T code in BSD systems, whereas in fact I don't think there was any. And at that time, there was a risk that BSD would become non-free either. And to make absolutely sure that this wouldn't happen, it didn't happen. BSD is still completely completely open source and free operating system, and to some extent even more free than Linux, I would say. But at that time, Linus Torvalds decided to implement yet another completely unrestricted by any previous licenses operating system, and he started working on Linux. So he had a design choice at that time. Either follow a fashionable approach advocated very much at that time by Tannenbaum at the University of Amsterdam and by the Mach team at the Carnegie Mellon, and create a microkernel. or create a monolithic kernel BSD-like. So you know the result? He created a monolithic kernel in spite of all this microkernel hype which occurred precisely at that time. And there is even a remark, it was known that Linus Torvalds, when he did it, he was still a student. He was a fourth year student in 1991 when the first Linux kernel was released. Do you remember which month was it? The birthday of Linux. October 91. So at that time, Andrew Tannenbaum, he said, if Linus Torvalds were my student at University of Amsterdam, he would not get a good mark from me for his coursework because he opted for monolithic kernel development rather than a microkernel, and only microkernels are the right thing. Nevertheless, Linux had a tremendous success, and not only Linux, but even older style monolithic BSD systems have also been a very, very, very big success. So, for example, um, OpenBSD was the first really security conscious operating system. So it has emphasis on security. Everyone nowadays uses SSH, right? How do you log in into a remote system? If you need a remote login, you use SSH, right? And you take it for granted that when you need to access a remote system, it is via SSH. All right? Please, your feedback. What do you think about SSH?
What feature of SSH?
Okay, are you using SSH for remote logins?
Yes.
Okay. And it is something like we have always been using and we take it for granted. Not true. SSH as a security feature only appeared to be, and that is why it is called OpenSSH, in the OpenBSD operating system, and it was very closely and still very closely integrated with OpenBSD. Previously, and that was the case even not so long time ago, maybe 20 years ago, instead of SSH, people were using insecure protocols such as Telnet and FTP without any cryptographic security. And it was completely normal that when you use Telnet, you send the password unencrypted to the remote server, and therefore any man in the middle, just any admin who operates a router anywhere in between you and remote location would be able to intercept this password and then break into your server system. You know, it is extremely difficult to imagine, but that was the case. So OpenBSD gave us security. Uh, for example, uh, many other good ideas coming from the BSD operating system, uh, they're still very widely used. So all of them, BSD for sockets and security, Linux for what we use it every day, Mach for threads, they all have been very important founding stones of modern operating systems. And being originally monolithic, Linux kernel also evolved very much. although we can't see it, but it is also a kind of microkernel nowadays. Only the processes which you create in a Linux kernel, they are a little bit more difficult to see. But in fact, they follow the microkernel idea. Let me even show you something. Okay, so I stop this and I do another screen at the moment. So let's do something. Um, for example, this one. Can you see my screen?
Yes, Professor, we can.
Okay. So let's see which processes are currently running in this system. In Unix, in Linux, there is a very nice command which is called ps3, which shows the process as a tree. So we see quite a lot. Can you see them? So for example,
Yes, we can.
network manager and so on. Actually, when a Unix system starts, there is only one process which is created immediately. It is a so-called init process. This init process, it still exists somewhere, I think. So it is here as bin init. So the image of this process, the executable from which this init is still there. But as you could see, it is now a symlink. So it is not an init. It is now in modern Linux systems, it is called systemd. And this process received the process ID of 1. So it is number 1. If we use, for example, the top command, then the process ID is on the left, PID, process ID. So here is our init, systemd. You can see it, right? Systemd, number 1. But what are other processes you see? For example, number 2, 3, 4, 6, those ones. These are all processes automatically created by the kernel. They are not created by the user. They are not created from within init. Because in the old style Linux and Unix process, the number 1 and the only one initially process was init, and then init was so-called forking. A fork is a Unix system call. We're going to talk about it later, which basically splits a process into two. The next one appears to be under a new process ID, and then it is able to execute a different code if it likes. And that's how the whole tree, the whole hierarchy of process is created. Not so anymore. The processes like number 2, 3, and so on, and until about 50 or 100, they're kernel-like processes which are automatically created, but nevertheless, they get the same visibility from outside. They have process IDs. You can even to some extent communicate with them if you are out. So for example, you may assign those processes to a particular CPU and so on and so on. And those are precisely kernel internal processes which implement different types of schedulable functionality within the kernel, which means that even though it is a monolithic object nowadays, a Linux kernel, but dynamically it still uses the same microkernel ideology now. And that happened about, I would say, to a full extent. That happened in Linux kernels of version 2.4 something. 2.4 kernels are of very early 21st century, not very early, 2003, 2004. I think at about that time. In 2.4 kernels, this microkernel ideology was internally adopted by the Linux kernel as well. So actually, to a very large extent, Mach philosophy, Mach ideology is now in a large number of operating systems, not only those which are direct descendants of Mach, not only in L3 and L4 microkernels, but even Linux was to a very large extent affected by Mach. So that really appeared to be a right thing, although implementations are completely different and dissimilar to each other. Okay, so that's about this class of systems. Yet there are many other operating systems. L3, L4, we are going to talk about them. They are largely experimental microkernels, but still highly important. There is another important family of operating systems which we need to talk about, which are called real-time operating systems. So what are, if you have heard about this concept, so can you say what is a real-time operating system?
It's operating systems that dedicated to serve real-time applications.
Okay, and what are real-time applications which we serve with them?
Mm, like medical applications or military ones.
Let us say real-time applications are those which need to provide a response within some guaranteed deadline. All right? And indeed, it could be a life support machine, which must really provide operations in a timely way, and therefore the controller of this medical application must have a real-time response. Or it could be avionics, it could be another type of military or space applications. In general, real-time operating systems control some processes, real life process, like, for example, engines or medical equipment or nuclear devices or whatever, which operate in physical real time. And therefore, the response of this operating system must also come within, and that's the key word, the whole idea, within a predictable time. It doesn't really mean that real-time systems, by definition, must provide a very fast response. It may or may not. But what is important is that they must provide a completely predictable real-time response. Now, from your experience, is Linux a real-time operating system?
No.
No. Uh, in general, no, although Linux evolves to be a real-time operating system. What are typical examples of Linux when you really know that it is not real-time? So what kind of non-real-time response would you get from Linux? Have you observed any kind of non-real-time response from Linux?
The disk operations.
Disk operations, that's true. And even more, if, for example, instead of a disk, you use some slow media like flash pen drive, and you put a large file on it, and then you try to synchronize the operating system. Then, well, yes and no. At least we don't know why it is not real time. It's not because it may take minutes. It might be normal for a large file to be written on slow media to take minutes. So the fact that it takes minutes, it doesn't really mean that it is not a real-time operating system. It might be an operation which really just physically, it's physically slow media after all, which physically takes that much time. But the problem is that there is no estimate. We can't predict this time. We can't say, okay, it will definitely complete under 3 minutes. 3 minutes are okay, for example. But we must know this figure, 3 minutes, and not a single second longer. But there are no such figures in Linux. So Linux response, although it is normally fast, it is unpredictable. It is actually becoming more and more and more predictable over time. So first of all, even in normal Linux, I would still classify Linux as, first of all, real-time requirements are also divided into 3 groups. There are hard real-time, firm real-time, and soft real-time. And I will explain in a second the key concepts behind real-time operations. So suppose that there is a certain task, process, thread, activity, function invocation, whatever, any unit of activity which is supposed to deliver a certain value. And it must complete within a certain period of time. So for example, if we, as I did now, for example, during the break between our lectures, my Zoom implementation was compressing the previously recorded lecture. That's a kind of just unit of activity. It took longer than anticipated. Is it a kind of, and finally, obviously, there is a non-real-time activity. Eventually, I got it compressed. That I got it compressed means that I would be able to upload it to YouTube and will have some kind of value, because you and also me would be able to review our first lecture. So after it had completed, it has some value. So the question is, the fact that it overran the time, I expected it to be in 15 minutes, it took more. Can we say that the value delivered by this this stream compressor diminished as a result? I don't know, probably not. So because the value did not diminish depending on completion time, so let's T is a completion time, and this is the value of activity. Of activity. If the value of activity does not depend on completion time, stays more or less the same, it is non-real time. If the value of our activity may decrease and may even tend to 0 but never become 0, depending on completion time, it is soft real time. It is like, I don't know, delivering a pizza. When you get it, the sooner you get it, the better. It is still warm. Even if you got it after 1 hour, after it has been delivered, it probably still has a value for you, but the value is less. And you need to warm it up again. Okay? Firm real time are those which not only have the value decreased, but the value decreases to 0 after some time. So there is a deadline, and if this deadline is not met, then the value of a firm real-time task is 0 anymore. It's like your real-time task, a firm real-time task, is to submit a paper to a conference before the deadline. If you didn't meet the deadline, then what you have done so far becomes of 0 value because the deadline is missed, and you, well, maybe not completely 0 because you can resubmit for another conference, but at least for this conference it is 0, and you can't do anything since then. From this diagram, can you guess what is a hard real time then? You see, non-real time, the value is constant, doesn't depend on completion time. Soft real time, the value diminishes or decreases, but still remains positive, depending on completion time. Firm real time, the value drops to 0 at some point, which is a deadline. So what is the hard real time then?
Probably depends linearly.
Sorry, repeat please.
Probably the value depends linearly on the completion time.
Oh no, it's much more than that. It's not linear here either. Well, linearly you are right in some to some extent, which means that the value can become negative. That's the very important thing. It may be linear or non-linear, but in case of a deadline overrun, it becomes negative. What does it mean become negative? It means that the deadline overrun has produced some damage. If it is our hard real-time processes engine control in an avionics system installed on an aircraft, the deadline has overrun, therefore some malfunctioning occurred with the engine stops, and in the best case, our airplane has to return to the airport of origin. In the worst case, an air disaster can occur. So that's definitely a negative value. So a real-time operating system may or may not be capable of running tasks belonging to those different criticality levels. So Linux currently is definitely capable of running soft and maybe firm real-time tasks. It evolves towards more and more and more predictability of its response time. Prior to, and that's a very important, prior to 2011, there was such an entity in the Linux kernel, which was called a big kernel lock. If you're familiar with the principles of concurrent operations, it means that a process which would lock in this big kernel lock would preclude any other processes from acquiring this lock until and unless the process who actually got access to it would relinquish it, which means that potentially one process could stop any other process for an indefinite period of time, for a completely unlimited time. That is the impact of the big kernel lock. this is the biggest no-no for real-time operations. But big kernel lock is gone, not in since 2011, and actually the occurrences of places in the Linux kernel where this big kernel lock was being used, there were already very few, even in 2011, but in the original Linux system, it was used quite permanently. So, which means that a single process which does something maybe wrong, maybe unintentional, maybe intentional, could freeze the whole, maybe the rest of the system. If many processes and many entities within the kernel use this big kernel lock, then any misbehaving entity, by locking it and failing to unlock it, could freeze the rest of the system. All right. The less it is used, the more we are moving towards a real-time like operation. So when this big kernel lock was completely eliminated, this opened the way of uh, using Linux as a true real-time operating system. There is a patch to the Linux kernel. What we get as a standard, or we call it vanilla Linux kernel, is not the full set of possibilities we may have. There are third-party patches to the Linux kernel, and one of them is called preempt-RT. Preempt-RT patch. So when it is fully incorporated into Linux kernel, Linux will become a fully real-time operating system. What does it mean, preempt-RT? Preemption means that any process which has, for example, by design, a higher priority than another process, may preempt that lower priority process and become active and take control over the CPU based on a particular scheduling policy. So, for example, if it is a priority-based scheduling, then a higher priority process can freeze a lower priority process, get access to the CPU, run, for example, run to completion, and then release the lower priority CPU. That's completely normal. But a lower priority process may be in such a state, for example, being inside the kernel, performing the kernel call, that it is not preemptible at that point. So even if it has a lower priority, and yes, there are all reasons for it to be preempted, but it can't be preempted simply because of the kernel design. There are some sections of the kernel code which are simply not preemptible. If preempted, then this would result in a wrong execution of the corresponding section of code. This is not the same as a big kernel lock, because this would not be a single lock for all processes. But still, this particular process might not be preemptible at a particular point. The preempt-RT patch to the Linux kernel completely eliminates such a possibility, and each and every process can be preempted at any time without any restrictions. That's one. And number two, this also includes internal kernel processes, those which are related, for example, to device drivers. And this means that we are, at least in theory, able to predict the response time of any process running within Linux. If, at least in theory, we're able to predict the response time, then it means that Linux would become an operating system suitable not only for soft and firm, but possibly also hard real-time operations. This preempt-RT patch, it is big. it has been created by the industry outside of the Linux community, and then gradually being absorbed into the mainline vanilla Linux kernels. So now most of this preempt RT patch functionality is already inside the Linux kernel. So you can create, for example, processes with real-time priorities, real-time scheduling within Linux, but still not completely yet. So we are waiting with each next Linux kernel release. There are promises that preempt RT patch would finally completely go into the standard vanilla Linux kernel, and therefore it would become a real-time, fully real-time operating system. The last time it was promised for January this year. I think it didn't happen yet. It was blamed on obviously on coronavirus pandemic, although it is not completely clear why coronavirus could affect the Linux kernel development and how. More likely it is just a normal. It wasn't, you say? I don't think it was, yes. Most likely it was just a natural complexity of this patch incorporation, but I really hope that this year we'll see its full integration. For the moment, if you want a fully real-time Linux, you need to install this preempt RT patch separately and amend the kernel, and then recompile the kernel. So once again, this is the reason why you really need to be able to recompile the Linux kernel. So obviously, this predictability comes at a cost. It might even be, and it is typically the case, that without this predictability, on average, your response time from the operating system would even be faster. It is on average faster, but in the worst case, unbounded from above. So we would have for the response time, by response time, we would see something like, for example, sending through the kernel a message of a fixed size. You do a socket write or a socket send in this case, and we measure actually, for example, how long it takes in, let's say, nanoseconds or microseconds. It would typically be around 1 microsecond, possibly less. So we may have a distribution, and then we can search a distribution of this sending time. So this is time, this is a frequency. So it may very well be that a typical distribution would be like this. So in the vast majority of cases, it takes, for example, 1 microsecond. But then there is a tail, and it can take potentially long time, although let's say the mean and the mode and the median of your distribution are sufficiently small. So for example, here the mode of your distribution is 1 microsecond, the maximum of density. But still, with this type of distribution, is our operating system real time or not?
No.
No, because your socket writing operation can potentially, with low probability, yes, but potentially take an unlimited time. We don't know how far it stretches. On the other hand, if we apply this preempt RT patch to our Linux kernel, and then again measure this type of distribution over, let's say, data of the same size, we may observe the behavior of this type. So now the mode, the maximum density of your distribution is bigger. So suppose now it takes 2 microseconds. So in the majority of cases, the real-time operating system performs worse than a non-real-time operating system. It takes longer time, right? But in this case, unlike the previous one, your density, your frequency of those distribution times becomes zero at some threshold. So for example, here is 3 microseconds and no more. After 3 microseconds, we have absolute zero frequency, which means that it doesn't take more than microseconds. It takes 2 on average rather than, let's say, 1. So on average, it performs worse. But on the other hand, we have a full predictability. Which operating system would you prefer in this case? If you only have, let's say, up to firm real-time requirements, then it is, I think, perfectly good idea to select the first one, which is simply faster, on average faster. That it may very rarely, on very rare occasions, take long, that's okay in that case. But if you really have a hard real-time requirements, and you know that overrunning this deadline may produce damage rather than positive or at least non-negative utility, then you would go for the second one. And then you would really exercise full real-time mode within your operating system kernel. So you would configure it with full real-time support. Apart from Linux, there are other very well-known and really hard real-time operating systems which are used for real-time control. If it is a nuclear power plant, then I don't think it runs Linux with a preemptor RT. Still, because it is not mature yet. Real-time operating systems, apart from Linux, with possibly preemptor RT patch, are the following. You have probably heard about QNX or QNX, and most importantly, about VxWorks. And there is a very interesting real-time operating system, which I encourage you, maybe we'll have some time to have a look at it. It's beautiful by design because it provides very lightweight and efficient mechanisms for inter-process communications, which is very important for real-time operating systems, inter-thread, inter-process communications. This operating system is called RTEMS. Have you heard about it, by the way, RTEMS? If not, have a look at rtems.com, rtems, yes, .com, and rtems.org sites. RTEMS stands for real-time, RT is for real-time, E for executive, real-time executive. You remember what executive is at the beginning of the first lecture?
Kernel.
Executive is the same as operating system. Yes, kernel or operating system, but primarily with application to real-time and embedded operating systems. Yes, real-time kernel, you can say. A real-time executive for some kind of M systems. Nowadays, M stands for multiprocessor, but previously, when RTEMS was in its infancy, and it was really first created also around in late 1980s. Actually, evolution of the operating systems is slow. Linux is 30 years old this year, 30 years old. In October 2021, Linux will be 30 years old. Mach is even older. Unix in general, going back to the original Unisys, is already 50 years old. Artems is 30 plus. So originally M stood for military and even more so for missile. It was an operating system designed for a control unit, for real-time control unit of the United States MX Peacekeeper ICBM, Intercontinental Ballistic Missile. Interestingly enough, although I could guess some and probably many aspects of the design of this missile were top secret, the operating system itself is not. Apart from, of course, device drivers for military hardware, which it was controlling. But the operating system as a kernel, as the executive, was open sourced by the US Department of Defense, and it is still used as a very good open source operating system, real-time operating system. It was originally implemented in Ada, in the Ada programming language, and the reason is until 1997, Ada was a mandatory programming language, programming technology, which had to be used for all US Department of Defense projects, software projects. So whatever software system you were implementing for the US Department of Defense, it had to be written in Ada. This mandate was revoked in 1997, and indeed, implementing the kernel in Ada was a little bit tedious, although possible. That was with Artems version 3. Now Artems 4 was already implemented in C and appeared to be easy and more lightweight than the Ada version. Although I still probably regret to some extent that Ada version is gone. It was really interesting. And now it is Artems 5, which was released very recently. The development is slow. It is not backed by the US military anymore. It is a community-driven effort. But if you look for a very good high-performance operating system, for example, for your robotics application, for example, or for may even be an autonomous driving vehicle for unmanned aerial vehicle, then Artems is still a very, very, very good option. The major problem with Artems is that it is still 32-bit. For the majority of CPUs, it is cross CPU, it is available for a number of processors. Mostly it is 32-bit. For x86-64, it is Artems 5, only Artems 5, which supports it, and the support is very, 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 very poor. It has almost no device driver, so almost nothing. Whereas for 32-bit, it is quite a comprehensive and nice operating system. And real-time capabilities, moreover, not just real-time capabilities, but very good real-time capabilities based on formal proofs. That's why we're going about formal verification. They do exist in the operating system SCL4. So this one is a real-time operating system as well. So I think I painted some kind of picture what modern operating systems are about. There are many microkernels, nanokernels, so-called library operating systems nowadays which provide a bare bones support for particular uh, maybe language environments and so on. The major problem with a very large number of experimental research academic operating systems is simply lack of device drivers. So there is an operating system with very good properties. It is a microkernel or even a more lightweight nanokernel, picokernel, exakernel, whatever. And then you think, okay, I would like to use it. And the problem is it only runs on a virtual machine. It would only run on an emulator like Camel. But that's no point. And those which are comprehensive enough run on a sufficiently wide spectrum of hardware are not that many. Yes, it's L4, although it has some limitations with hardware support. Obviously, BSD systems are most widely ported. So if you want your general purpose open source operating system to run, let's say, on some kind of obscure MIPS platform, then the chances are Linux may or may not run on it. But NetBSD will run on it because NetBSD has been ported to a very vast number of hardware architectures. So the BSD family, at least from this portability point of view, is still very important. Interestingly enough, even Minix is used not only in academia for teaching microkernel concepts, but it is used in the industry. You know that, suppose that, okay, you buy a PC motherboard, okay, you put a CPU on this motherboard, but there are lots of other chips. So for example, there are North Bridge, South Bridge, and now they're integrated into a single IO chips, which provides control over all IO functionality, input-output functionality, peripheral devices of this motherboard. It's interesting that this control chip is still not a hardware embedded logic. It still runs an operating system on it. And that operating system, interestingly enough, is Minix. So all operating systems we have discussed so far, they provided some interesting impact on modern computer science, interesting ideas. We examined a family tree of them. So maybe in the next lecture, before moving, next lecture is tomorrow, before moving further, we will have a look at how you can recompile and boot the Linux operating system, because I think this is a kind of hands-on skill which is important for all serious computer scientists, for all serious software engineers. Once in a while you need to do it. So we had 2 lectures today. Tomorrow we'll have, at least in the first half, a practical session on working with Linux kernel. Okay?
Okay, Professor. But I have a question about the syllabus. Would
Okay,
you put the syllabus on Moodle?
I will, yes. It may evolve a little bit because I just will reconsider it a little bit based on our discussions today. But I will definitely put it. Maybe not before tomorrow, but at least before we meet next week. Because what not only you learned something from me, I also learned from your background and your experience about probably some alternations to the structure of our model. So I will tweak little bit our syllabus, and it will be in before Friday next week. I can't promise before tomorrow, but before next week it will be in. Okay.
Okay, thank you very much, Professor.
Okay, thank you. My pleasure. And
Um,
we meet tomorrow on Zoom again. Yes.
may I?
Oh yes, yes, please, yes.
Okay. Sorry. Could you please tell us about the grading policy for this course? The
Grading
projects
policy,
and
it will be in syllabus as well. I presume. You see, this is MSc level module, so we have no labs. Whether it is a good idea to do a midpoint exam, would you like to have a midpoint exam, actually, midterm? We can do without it. How do you feel about 100% of marks being allocated into the final exam? Is it okay or not quite okay?
It depends on the exam.
It depends on the exam, but in general, that, you know, we put just 100% in the final. I will think about it. It's just due to the structure of this course. It's a little bit difficult to do something else apart from that, but we'll see. Or it may be that you would do, although the labs are not provisioned, but you would do some kind of project. I think we will do that in this course, and then we'll be basing our final grade, let's say 30% on the project and 70% on the final exam, something like that. So I will make a decision and I will publish it along with the syllabus. But good question, thank you.
Thank you, sir.
Okay, thank you. So tomorrow working with Linux. Thank you.
Thank you. Goodbye.
Goodbye.
Bye.
Thank you, sir.